Good morning, everyone. Welcome to the lecture series of VLSI technology with the subject code KEC 053. So we were discussing the topic oxidation, and we have covered the process of oxidation, what is the need of oxidation in the last lecture. So this is the 11th lecture for this subject course, and today we are going to study about the growth kinetics of the oxidation. So let us see the glimpse of the last lecture. We have studied about what is oxidation, that when we grow some oxide layer over some silicon or germanium wafer, it is known as oxidation. And what is the need of oxidation? That we have to protect your number of MOSFETs, your number of devices on a single wafer. So and it acts as a passivation layer, it acts as a dielectric layer. So there are n number of needs for the oxidation. So for this growth kinetics of oxidation, we have studied this deal groove model method, where we have segregated the portions into three parts, that is your gas, oxide and silicon layer, right? We have seen that we have this silicon substrate. We have the silicon substrate. Over that, some oxide layer is already there. We believe that some oxide layer is already there. So this is your oxide interface. And over that we will pass the gases. So these gases will react with this interface. These gas molecules then diffuse over this interface and then react with the silicon. So we have three parts: gas, oxide and silicon, right? So when they travel from one medium to another medium, they will have some flux. So this flux F1 in the gaseous region, it will be equal to Hg Cg minus Cs, where Hg is the gas phase mass transfer constant, Cg is the concentration of oxide species in gaseous form, Cs is the concentration of oxide species at this interface. Now, by this gas law, if we replace Cg and Cs by partial pressure of these oxiding species, we replace this by Pv is equal to Kt. This F1 we can write it as Hg divided by Kt, Pg minus Ps, where Pg is the partial pressure at this point at gas level, and S is the partial pressure at this substrate end. If we include the Henry's law, C equivalent, that is your equivalent concentration of oxidizing species, it will be equal to HPG, and we can write it as F1 Hg HKT C equilibrium concentration minus C naught, where C naught is the concentration of oxide species at the outer end and Ci is the concentration of oxide species at the inner side. So C naught we can write it as HPS. So these all equations we have studied in the last class. So as per the Deal's groove model method, this is the perfect generalized solution when silicon is getting oxidized, when we are growing the silicon oxide over the silicon layer. So first of all, when we have this oxidizing species in the gas stream, it must be transferred to the oxide gas interface, right? So we had this diagram, we have this gas, oxide and silicon substrate, right? So your gases will react with this oxide gas interface. So once these oxidizing species have reached the gas oxide interface, they must diffuse through the existing layer. They will travel through this existing layer and will reach to the silicon and oxide interface. The oxidation is taking place by the movement inside of the oxidizing species. So if they want to react with the silicon, they must move through the already existing oxide layer. We believe that before the oxidation start, there is a thin layer of oxide which is already grown over the silicon. So these gas particles will travel through that oxide layer, already existing oxide layer, into the silicon dioxide interface, and once these oxidizing species reach at this interface, they will react with the silicon wafer. So at second, your second flux equation is denoted by d C naught minus Ci x. So that was C naught minus Ci. We have this gas, oxide, and silicon. Here we have the Cg, Cs, C naught, and Ci, right? So we are writing this flux equation for this F2, this area F2. Here F1 is the flux equation and F3 in the silicon part. So for this area, for this much area, we can write the flux equation as d C naught minus Ci divided by x, where x is the oxide thickness which is already grown, and C naught is the concentration of oxidizing species at the outer end, and Ci is the concentration of oxide species at the inner end. And F3, at F3 we write the equation as Ks Ci, where Ks is the reaction constant and Ci is the concentration of oxide species at the inner side. So this equation is directly proportional to the oxide species which is present at the inner side, and how much silicon is already present in the wafer, that depends, that will affect this flux equation. So when we equate these two equations, we are going to have this Ci is equal to C naught 1 plus Ks x divided by d. This equation we already have covered in the last class. So F3 we can write it as Ks C naught divided by 1 plus Ks x divided by d. And from the above equation, we have the equilibrium constant C star. This is the equilibrium constant. Ks is the reaction rate. H is the gas phase mass transfer coefficient. D is the diffusion coefficient. X is the existing oxide layer thickness. So now if we combine these equations, we are going to have these two major equations for Ci and C naught. These Ci and C naught in terms of equilibrium constant. So here we can introduce two cases. All these mathematical modeling can be examined physically, that how they will affect physically the oxide layer. So we can have two cases. One is when your d, that is your diffusion coefficient, this d tends to 0. If this tends to 0, your denominator factor, this factor will be very large, right? This factor will be very large, and here, and this is also dominating in numerator side also. So this Ci will be very small and Ci will tend to approach 0. That is why we have this downfall in the graph. In the graph we have seen that there is a downfall from C naught to Ci. So this Ci will tend to approach to 0. And what will be the so Ci will be 0. Now what will be the effect on C naught? If your d tends to 0, this Ksd, this factor is dominated in both numerator and denominator side. So C naught will also approach to C equilibrium, concentration at equilibrium. So and Ci tends to 0. So this is the case when your diffusion coefficient d tends to 0. So we have a steep fall from Cs to Ci. So this type of oxidation is known as diffusion limited. Here the diffusion is controlling the oxidation process. The thicker the oxide layer, the more difficult it become. It will be the diffusion process to take place, right? So the more thick we have the oxide layer, it is hard to diffuse the components. So next case is when your d, diffusion coefficient, is approached to infinity. Then this factor, if this is infinity, this approaches to infinity, this factor will be very small, right? So here in this case, this will be very small as we approach this to infinity. So in the above equation, your numerator and denominator will be affected, and Ci will be equal to this concentration at equilibrium state divided by 1 plus Ks divided by H. So, and C naught will be equal to Ci. So in other words, we can say that there is no difference between the concentration of oxidizing species from the outer space to the inner space. So that is the physical speaking. If the availability or the diffusion of oxidizing species through the oxide is not posing a problem. The problem is after oxidizing species reach the interface. So this is the interface. So when your D approaches to infinity, we will have C naught that is nearly equal to Ci, right? So the problem is when your oxidizing species reach at this interface, how fast the growth will take place. This is obviously dependent on the availability of silicon. If your silicon is heavily doped, the growth process will be very fast, and if your silicon is slightly doped, the growth process will be slow. So this is how fast they react with the silicon. That is what going to govern the oxidation rate. So this is the case for reaction limited when your D diffusion coefficient approaches to infinity. So we have seen that when your D tends to 0, we have the diffusion limited reaction, and when your D tends to infinity, we have the reaction limited reaction. We have the reaction limited process. So now next step is to find out the growth rate, that what will include the and that will include the number of molecules of oxygen or water used in the oxidation reaction. So before starting the growth kinetics, we have seen that your silicon dioxide is either formed by oxygen molecules or by hydrogen by water vapors, right? So when your one particle of silicon is reacted with one molecule of oxygen, you will have one molecule of silicon dioxide. But in case of water molecules, when one molecule of silicon is reacted with two particles of water, we will have silicon dioxide and hydrogen gas as a residual, right? So now we will include the factor N1, that is the number of molecules. It can be either of oxygen or water vapors per unit volume. So the number of oxygen molecules per unit volume of oxide. How much is the number of oxidant molecules per unit volume of oxide? So obviously, if you are using the oxygen being the oxidant molecule, we need to have only one molecule, and if we are using the water particles, we will double that number. So for example, we are using this for oxygen. So N1 will be equal to 2.2 into 10 raised to the power 22, and for water it is going to be double, where N1 is the number of oxidant molecules that are incorporated in per unit volume. Dx by dt will define the growth rate. So we can write it as N1 dx by dt is the flux of oxidizing species. So because we know that under steady state condition, all flux values are equal, F1 is equal to F2 is equal to F3. So we can write it as this growth rate N1 dx by dt is equal to F3. So which is written as Ks equilibrium concentration divided by 1 plus Ks by H plus Ks x divided by D, right? So we have this differential equation. We can solve this differential equation to calculate the growth characteristics, that what is the rate of oxidation is taking place, how much thickness is achieved within a given time limit. So if you integrate these values, you are going to have this equation, and we will write here P as a integration constant. To evaluate the integration constant, this value P, to evaluate this integration constant, now we are going to focus on the initial state. We believe that before your oxidation process starts, there is a already grown oxide layer, right? So when we start the oxidation process, let us assume that silicon already had a initial oxide thickness present on it. So that is the most general case, right? So the initial thickness could be 0, and we can assume that it is also not 0. So xi is the initial oxide thickness. P, that can be evaluated by putting t is equal to 0 and xi is equal to x, and then divide the equation, this above equation, by 2d divided by ks. We are going to have this equation. We can simplify this equation by putting some constants in this, where a is equal to 2d 1 divided by ks plus 1 upon h, this factor, this is your a factor, and b is written as 2 diffusion coefficient equilibrium concentration divided by n1, this is your b factor, and tau is xi square plus axi divided by b. So this equation that is your x square plus ax is equal to b t plus tau, where the value of a and b is dependent on these factors. So this equation is the most famous Deal and Groove oxidation kinetics equation, which is used to predict the growth thermal oxide on silicon very accurately. So this is the basic equation which will be used till now to calculate the oxide thickness in the thermal oxidation process. So in order to find out the roots of this quadratic equation, we have this quadratic equation, right? So we have this quadratic equation, that is x square plus ax is equal to b t minus t plus tau. So we can find out the roots of this quadratic equation. Obviously we are going to have two roots, plus and minus. We will neglect this minus root because it will give you the oxidation process in negative direction, which is not practically possible. So we are going to have only one root. So now let us consider the two limiting case. The first case is when your value of t is very small. So the value of t is very small. So oxidation for a small duration of time, that is t tends to 0, actually not 0, it is the for a very small duration of time. So this value, the value of x, we will be having b t plus tau divided by a, right? So we can say that this is linearly proportional to the oxide thickness. Your oxide thickness is linearly proportional to this b upon a factor. Next case, when your t is infinity. So when your time approaches from 0 to infinity, when you increase the oxidation time, the x, this t approaches to this factor is infinity. So this will be very large and x will be equal to under root of bt. So this will give you a parabolic rate constant. So this is the famous Deal-Groove linear parabolic equation of oxide growth rate and linear parabolic. That is, when your oxidation time is short, the growth rate follows the linear rate of increase, and when your time is much larger, it follows the parabolic rate of growth. So so this is called the linear parabolic rate of growth, and this is very important equation for governing the growth rate. So this is the equation which we are going to learn, which we are going to use for the oxidation process. That is, x square is equal to ax is equal x square plus ax is equal to b t plus tau, where a, b and tau having their significance and they are dependent on various constant. So so this is the general growth rate equation. So this graph shows the value of B and B by A versus temperature for dry oxygen and wet oxidation rate. steam oxidation is none other than wet oxidation rate. So we can see that each will have it is the temperature, we have the x-axis and the growth profile at the right axis, right? So we will have this when the factor of B at dry, when your dry oxidation is taking place, and the factor of B when we have the steam oxidation, wet oxidation is taking place. So we can see that in case of wet oxidation we have the more growth, right? And in case of dry oxidation we have the less growth. Similarly, for this factor B upon A factor, which is dependent on some another factors, so we can see that for dry oxygen we have the less growth rate, and for wet oxygen we have the more growth rate. So the value of this B and B by A for dry oxygen and for steam oxidation method is seen by this graph. Next is the silicon oxide thickness with respect to time, that how much oxide layer is grown with respect to time. As we have seen earlier, the oxidation process is a process of diffusion of oxygen or hydrogen ions into the silicon dioxide to reach the silicon dioxide silicon interface, and then they will react with the silicon to form the silicon dioxide. So as the thickness of the silicon dioxide is increased, the rate of diffusion become slower, right? The more thick we have the oxide, the more difficult will be the diffusion, right? So the more difficult will be the diffusion. The more thicker is the oxide layer, the insulator layer, the more difficult is the diffusion. So in the initial growth process, the rate of thickness is directly proportional to the time of growth. We have seen in the previous slides. And however, after certain point of time, the thickness of oxide is proportional to the square root of the growth, that is your parabolic growth. So we can see in the graph that for a very small duration of time, we have the linear growth, which is dependent on B upon A T, and after that when we increase the oxidation time, we are going to have the parabolic increase, right? So it is dependent on square root of B into time. Next is their wet oxidation growth and dry oxidation growth. Out of this wet oxidation growth and dry oxidation method, your wet oxidation method will give you higher, it's used to grow the thicker oxide, because your wet oxide growth method has the higher rate of growth as compared to dry oxide method. It is because your hydroxide ions have the higher diffusivity than the oxygen molecules in silicon dioxide. So the result also shows the higher temperature has the higher growth rate due to the higher diffusivity. So we can see in the diagram, this is the graph for the which is achieved for the silicon dry oxidation process, and this is the graph when we do the oxidation process in the presence of water vapors. So we can see here that for maximum temperature, that is your 1200 degree C, we have approximate 1 Armstrong thickness layer, 1 micron thickness layer, right? Approximately 1.0 micron. And whereas in case of oxidation, wet oxidation, up to this for this 1150 temperature, we have more than 3 microns thickness layer, right? So this is the reason, because the OH ions can diffuse very quickly as compared to your oxygen molecules. So next is your growth rate of silicon is also dependent on the crystal orientation. Crystal orientation of silicon. Your silicon crystal orientation with 111 has the higher oxidation formation as compared to your 100 orientation. That is because of the fact that your surface density of 111 orientation is higher than the 100 orientation, and the rate of silicon dioxide formation is also dependent on the temperature of the oxidation. The temperature diffusivity is given by the equation. Your diffusion is equal to d naught exponential of minus EA divided by KT, where D naught is the intrinsic diffusivity and EA is the activation energy. Lastly, this diffusion rate is also dependent on dopant and doping concentration of silicon. Generally, the heavily doped silicon will grow the oxide layer very quickly as compared to your lightly doped silicon. So, this graph shows the doping effect of dopants on the oxide layer. So, during oxidation, your boron tends to draw upon to the silicon dioxide and cause the depletion of the boron concentration at the silicon dioxide interface, which results in thinner silicon dioxide layer when your silicon is n-type doped. So, n-type dopants such as phosphorus, arsenic or antimony have the opposite effect. The doping concentration at the silicon at the interface is higher than the original doping concentration due to this pile-up effect of the dopants at the interface. So, as a result, thicker oxide layer will be grown when we have this type of dopants. Okay. So, at here we can see that original doping concentration is less, and we have this graph because of your p-type silicon, and in case of this we have this original concentration, and we have seen this pile-up effect because your dopant concentration of n-type silicon, and we know that n-type silicon is heavily doped as compared to your p-type silicon. So, this is all for today's lecture. In today's lecture we have seen the growth mechanism of oxide layer, how we can calculate the roots with the help of roots of a quadratic equation, how we can see that for a small duration of time your growth is taken linearly, and when you increase the process time, oxidation time, your oxide layer will grow in a parabolic way, right? And secondly, how the orientation affects the growth rate, how the wet and dry oxidation is taking places, and which one is used to grow the thicker oxide and thinner oxides. So, in case of out of dry oxidation and wet oxidation, wet is used to grow the thick oxide and dry is used to grow the thin oxide layer. And lastly, what is the effect of impurities on the and the substrate on the oxide layer growth. So, thank you very much for today's lecture.